Okay, so in section 5.1, we talked about the area under the curve, and that can be told as the integral. And we could find them with a series of what's called Riemann sums, where you used the rectangular approximation method. So let's change colors. We drew our rectangles in here. Right now I'm using a LRAM with my points on the left side. Okay, and we know that the area in both cases is positive. However, when it is below the axis, this will give us negative values. Okay, so if you want the area, you end up having to just make that part positive. Take that negative thing, make it positive. So, by definition, this is a sum of the area of a bunch of rectangles. So, you can say that this is the limit, the definite integral, which is what we're going, is going to be the exact area. So does the limit as n approaches infinity of my delta x, which is this. So n is essentially my, there's an infinite number. So delta x is essentially the width. My total size is divided by the total thing. So it's a sum using a sum formula where we're going to add them all up from k equals 1 to n. And we're going to pretend, so it's whatever this function is. So it's f of m of k times the width of my rectangle. So it's my function times the individual value plugged in for each one of these times the width of the rectangles. Delta x, my drawing's not perfect, but you can assume those are all uniform width. And the notation for this, so this is a definite integral of f of x dx, and we can put boundaries on this. So the boundaries would be a to b. B is the end point. So an interval notation that goes from A to B. Okay. This is a little bit of a new notation. The definite integral is what this thing is called. This little shape, boundaries A to B, it's called lower bound, upper bound. And my function always has to be of D, my independent variable. And you can think about that in terms of something like this. You can think about that in terms of something like you say you've got a derivative. Well, if I multiply both sides by dx, I have dy equals 2x dx. Integrals end up being the reverse of derivatives, when I get rid of the dy dx part, I can take the integrals. Okay, that's coming next chapter, but that's an important thing. It's also important to understand, and we'll get to this later when we've done some integrals, this idea of the integral being the sum of the infinite RAM boxes. Okay, and we'll get to how to translate between those later. Okay, we're going to do some examples with what an integral looks like. I'll teach you how to do it with your calculator. You'll have to be able to do them by hand too, but the calculator can do them, which is very nice. So this, we always have to have the dx. If I understand what this is a semicircle with a radius 2. So I could have something like y equals square root of 4 minus x squared. If I square both sides, I get y squared equals 4 minus x squared. I add the x squared to both sides, giving me x squared plus y squared equals 4, which you should know by now is a circle of radius 2. This is only a semicircle because it was only the positive x squared, so it's this. So that's what this means. The area of a circle of radius 2, well, this is a semicircle, so it's half pi r squared. R was 2, so this ends up being 4 times 1/2 is 2 pi. I just did an area with geometry. Yes, sometimes you can do integrals with geometry. When you can, it's usually the easiest way. But often we don't have nice geometric curves that they fit. So, how do we do a definite integral? This is a pretty easy one. What's derivative is 75? Well, that derivative would be 75 t. I know my variable is t because it's dt. Okay, this is the derivative of whatever my independent variable was. So 75t we know has a derivative of 75. We'll do some basic ones, but only kind of really easy ones. So what does this mean? To do this, to get this area, I do upper minus what's called upper bound minus lower bound. The integral changed to a bracket from upper bound to lower bound. So 75 times 9 minus 75 times 7. I don't know what 75 times 9 is, but I know that the difference is 2, so it's 150. Okay, we'll really only be doing very, very basic ones. Kind of a shortcut rule for this is when you're taking of x to the n, so I'm not putting specific bounds on this. You normally we subtract one from the multiply by the exponent, subtract one from the exponent. Well, to reverse it, we have to add one to the exponent and divide by that new exponent, which is n plus 1. So add 1 to the exponent, divide by that new exponent. There's often also called this plus c. When you deal with, if you don't have bounds, you have to put a plus c on. If you do have bounds, bounds being these guys, there's no plus c. Plus c means a constant. So if I'm taking a derivative, let's say it's x to the fourth plus 7. Call that f of x. Its derivative is 4x cubed plus 0. Well, if I'm going backwards, I add 1 to the exponent. So I put my number, add 1 to the exponent, divide by the new exponent, which is x to the fourth. But I didn't have a plus 7, so we say there was an unknown constant. That constant could be 0, so it wouldn't be there at all. But there's a constant here that is by default added, and we just call it plus c. Under certain conditions, you can find what c is. There's only a plus c with no bounds. In the situations here where I don't have bounds. If I do have bounds, I do the plug-in. So, doing a definite integral via your calculator. I'm going to jump over and I'm going to share my screen. And we're going to go to the calculator app. So I just go to a regular old calculator screen. That's the graph. And I'm going to do the following integrals. So I'm sharing my screen. Following integrals are going to be done here. Oops, these are ones that would not be easy to do by hand necessarily. Notice there's always the dx or d something. So in order to do this, ignore the examples in the book because they're not going to help you. So I go menu, calculus, numerical integral. And I just type it in. So this is a trig function. It's very important that I need to do x times sine x dx. It's very important that I am in radian mode. Make sure you check whenever doing trig. Missing parentheses. Oh, what's those? 2.04. Okay, that was easy. Next one, menu, numerical integral. 0. Use the arrows to get around. 1. Or over 1 plus x squared dx. That looks like pi. 3.14159. I think that's pi. I believe that's it. The integral would be an inverse tangent. Oops, I didn't want a derivative. No, let's do our last one. Negative 0.886. And there we have that. Okay, we're going to talk about integrating a special function here. And that special function is going to be so in order to do this, we need to think about the graph. The absolute value of x over x is just like x over x, so it's 1, except when x is negative, in which case one of them is positive and one of them is negative. These are actually both open circles. So here I've got -1 and up here I've got 2. So I'm looking at these two areas. So this one has an area, it's 1 by 1, because this is -1, that's 1. Its integral is -1 because it's below the axis. This one has an 1 by 2 rectangle, has an area of 2, so that has an area that equals 1. Again, I'm thinking about it in terms of areas, not in terms of other things. I was just able to calculate the areas. And there we have it. That's section 5.2.